I'll just take few minutes time to talk about Lyapunov stability. Yesterday, while teaching Lyapunov stability, I gave you the concept of Lyapunov stability, and intentionally, I gave some wrong answers just to think over that because you are academics, okay? And I will pass on the other lecture handouts which will be circulated to you. Professor Rahul Kaur will circulate that, right? What is the things? While you teach the people of the students in your class, don't talk to them what I am going to talk now because they will unnecessarily get confused, right? What I teach last time, you just teach them. You see, I have got a nonlinear system. I have got a nonlinear system. Written that. Yeah. Now I have got a nonlinear system. X dot is equal to f of x. Right? I'll tell you. This particular system has got multiple equilibrium points. Multiple equilibrium points. Right? So what we do in linearization? We compute the Jacobian, each of the equilibrium point, we find out the eigenvalues, and we say whether the system is stable or system is unstable, right? Lyapunov stability, yesterday what I gave you the answer, the Lyapunov stability is we study entirely for all equilibrium points, which is not true. Lyapunov stability also is studied with respect to each of the equilibrium point. Got a point? For each of the equilibrium point, not all. But don't confuse the students, you see. Don't confuse the students. Each of the equilibrium points. The catch I will tell you what the difference. Otherwise, if that is the case, then what the difference between linearization and that one? There is some difference. I'm coming to that point. So what happens? See here, this definition, very careful see it. Consider the zero input nonlinear system x dot is equal to fx. So you will say that if it is zero input, is it applicable for any other input? Yes, it is possible. Because input is a function of the state variables, so this becomes essentially zero input. Assume that the system has got a unique equilibrium point at the origin. This is the assumption, right? But the system doesn't have a unique equilibrium point. System has multiple equilibrium points, right? So the question is, first thing I'll tell you, step number one, again repeating the point, while teaching the students, don't tell all these things because they will confuse. Step number one, transform the equilibrium point, any equilibrium point you are talking about, you are analyzing equilibrium point into the origin. First to do these things. Suppose you have got a system, it has got an equilibrium point say at +1, you transform that one into origin and change the equations. Just step one I am explaining here. Step one, I will come back again, see here. Given a dynamic system x dot is equal to fx, and equilibrium point x satisfies fx is equal to 0. To analyze Lyapunov stability at xc, we typically do a coordinate shift. So this has to be done for each of the equilibrium point. We first decide which equilibrium point you want to study stability. That equilibrium point may not be at origin. That equilibrium point may not have origin. If not in the origin, you transform it into origin by a suitable transformation by Z. Now this actual system is extradigital fx. Now the system which we are studying is not extradigital fx. It is z dot is equal to f z plus x e. Right? Now this particular system, the equilibrium point is always at origin because you have shifted it. Got my point? So the equilibrium point now shifted to origin by suitable transformation. Then you examine, then other things are straightforward. Okay? First thing, so each of the equilibrium point which you are interested, you transform it into origin and then do it. So in the standard Lyapunov theory, it is implicit. We assume that the origin the equilibrium point. We always assume the origin the equilibrium point, and with respect to that origin, everything we are doing it. Right? Now the next question is, very simple question. We can do it. Then what is the difference between that and the linearization method? What is the difference? Because you are trying to analyze the system stability around the equilibrium point by the linearization method. And here also you are analyzing the system if the system operates within the origin. Okay, origin is the equilibrium point now, right? But it's not the case. When you take a Lyapunov function, that Lyapunov function has got an area. If you plot it, so here what happens, I will just tell you these things, these are very subtle things actually. The origin is the equilibrium point, right? Linearization method, linearization method will tell you if the system operates within a small region, whether it's stable or not. Lyapunov stability is different. It is origin, no doubt about that. But what happens? First you assume a Lyapunov function, then you differentiate. If it is negative, system is stable, right? That Lyapunov function will decide by what range. This is the Vx function. That means if the system, suppose the system is stable, that means system is stable if you operate not around the equilibrium point, but in this particular region. Okay. So what happens, the students when they do the research, what they will say, I have got a system, I took this Lyapunov function, then I found the system is stable. Then another student will say, the same system, I took this Lyapunov function, this system is stable. That means the second person's approach is more better than this one. Another person will say, I took another Lyapunov function, this system is stable. It is not around the equilibrium point. It is around the area defined by the Lyapunov function. So for each of the equilibrium point, you have to find out what is the, whether it's stable or unstable. So here you see, I will pass on to you, all examples are here. This point is important. Lyapunov stability is always with respect to a specific equilibrium point. It is not, as I told you yesterday, not for all equilibrium points, specific equilibrium point. So the equilibrium point where you want to study the stability, first transform that equilibrium point to the origin. Then start analyzing it. Next point is how it is different from the linearization, because in linearization you are taking you are assuming the system operates within a small region, but here you don't assume that. Here you take a Lyapunov function, so the people say this is the stability information based on this Lyapunov function. By changing the Lyapunov function, the stability information may change. Got a point? So that is the point. Lyapunov stability is always with respect to a specific equilibrium point. We cannot say a system is Lyapunov stable in general unless we specify which equilibrium point is being considered, right? This is for you to know, but for the students, don't tell these things. You just assume that the system has got only one equilibrium point at the origin and analyze the stability. Got my point? So, therefore, I intentionally, when you asked, is it general? I told you it's general. No, it's not. Each equilibrium point, because that's a point, still more things are there I cannot discuss here. There is a basin of attraction you have to see. Each equilibrium point has got a basin of attraction. So the Vx region which you are taking, if it is covering the entire basin of attraction of that equilibrium point, that is always good. So, two examples I have given here. So this note will be passed to you. Don't read the other notes, right? Okay, now let's go. Unfortunately, no. No methods. Until 200, more than 150 years now. No other methods. No other methods have been developed. Feedback linearization. There is one thing that is called the Jacobian linearization. The linearization which you are talking in general, they are essentially Jacobian linearization. X dot is equal to fx. You find the Jacobian matrix del f over del x at x is equal to x star. X star is the equilibrium point. Okay? And then you start designing this thing, Jacobian linearization. You linearize the system around the equilibrium point. Okay. There is a nonlinear system. You assume, find the equilibrium points, Jacobian, all this. There is another niche one is the feedback linearization. It is completely different than the Jacobian linearization. Feedback linearization, what it will do, if the system has got some nonlinear element, the controller will completely remove that nonlinearity out, right? I'm giving the example first. Many nonlinear systems cannot be controlled effectively using linear control techniques, PID, LQR, due to intrinsic nonlinearity. The basic idea is to algebraically transform the system into linear one and apply the linear control techniques. Is it same as the conventional linearization? No. Feedback linearization is achieved by exact state transformation and feedback and complete cancellation. Now see the example here. Now here, x1 dot is equal to x2 and x2 dot is equal to minus ax1 minus cx1 cube plus u, right? Now, there is a component minus cx1q, nonlinear component, completely cancel it. You see, if I select u is equal to cx1q plus v is the new input, right? Then to cancel the nonlinear term minus cx1q, then this cancellation results in a linear system, you see. This cancellation will result x1 dot is equal to x2 and x2 dot is equal to minus ax2 minus bx2 plus v, and v now you design. V is your new control input, right? So in this case what you do, you completely cancel it. As I told you yesterday the analogy, earlier system is nonlinear, you ask them that you operate in this particular region, don't disturb other people, right? We just request the person, I know that you are an idiot, but please don't disturb other people. You should just operate within a small region, right? But here, no. You are an idiot, get out. Okay, completely cancellation, right? Now, then you design the controller. Any controller can be designed, doesn't matter. Again, you see, while fitting any models to a system, as I told you, you must decide why you are fitting the model. As I have told you, you must decide why you are fitting the models. Otherwise, modeling is not a fun, right? If you want to design an adaptive self-tuning controller, you represent the system by a discrete parametric model, right? Because you see the derivation starts from the discrete parametric models. If you want to design a state feedback controller, the system must be x state is equal to ax plus bu, not parametric model, right? Similarly, if you want to design a step feedback linearizing controller, the system must be represented by this structure. X dot is equal to fx plus gxu and y is equal to hx. Right? Now see here, this particular transformation is called the affine class of nonlinear system. Affine transformation or affine class of nonlinear system. X dot is equal to fx plus gx u. That u is important, no u dot. No u dot or no u square. If your system, nonlinear system has got u square, okay, then you make some arrangement, some transformation to bring it to u. The system must be represented in x dot is equal to fx plus gxu. Fx is nonlinear, gx may be nonlinear, but it will be u is important, you see here. This is u, no u square, no u dot, and y is equal to hx. And usually hx is a scalar. And pose the question whether there exists a state feedback controller alpha x plus beta x v which will make this system linear. I have got a nonlinear system, x dot is equal to fx plus gxu, y is equal to hx. And I have got a controller u is equal to alpha x plus beta x v. Is it possible to transform this system into a linear system, right? Now, I'll come to this point. Change of variables will come later on, just a minute. Is it possible to cancel the nonlinearities in every nonlinear system? Feedback linearizing controller, is it possible to do it for all systems? Or such cancellation is possible only in some class of nonlinear systems which satisfy certain structural property? I'm just reading these things here. To cancel a nonlinear term alpha x by subtraction, the control u and the nonlinearity alpha x must always appear together as u plus alpha x. See, I want to cancel something, right? I want to cancel something. If that nonlinearity is added, then I can subtract it. If it is multiplied, then I can divide it, right? That is what he is saying, right? To cancel a nonlinear term gamma x, which is multiplied, so you have to cancel it by division, then something different has to be done. This point will save. Thus, feedback can convert a nonlinear state equation into a controllable linear state equation by cancelling nonlinearities if the nonlinear system is represented by a nonlinear state equation of the form x dot is equal to ax plus b gamma x into u minus alpha x. Okay? So, see here, this is clear. If the state equation, you see x dot is equal to ax plus b gamma x into u minus alpha x is a nonlinear system, right? If the system is in this form, this point is extremely important, I am telling you. If it is in this form, now see if I make u is equal to alpha x plus beta x v, if I make u is equal to alpha x plus beta x v, where beta x is equal to gamma inverse x. Now what will happen? Can you just tell me? You see I am doing it here. X dot is equal to ax plus b gamma x, right? B gamma x into u minus alpha x. Now u minus alpha x is equal to beta x v. U minus alpha x is equal to beta x v. Now beta x, now beta x into gamma x is equal to identity, because beta x by gamma inverse. So naturally, if the system is in this form and you are using a controller like this, it will convert it into this one, right? Now then you design any controller. If the system is represented in this form, then by using a controller of the structure u is equal to alpha x plus beta x v, beta x is equal to gamma inverse v, you can convert it. Now suppose it is not in that form. Suppose it is not in that form. It is that form, it is quite straightforward. If it is not that form, it is quite straightforward, you can put it. If it is not in that form, let us see. Suppose the system is not in that form, not represented in this form. Can you apply a control law which can make it linear? Right? Now see, one thing I must emphasize here, the concept state variable model of a system is not unique. I will give an analogy to make it clear. State variable model of a system is not unique. You can have infinite number of possible things by suitable transformation. Say for example, x dot is equal to ax plus bu. You can define a function, another variable x is equal to pz or z is equal to p inverse x. You can define another variable. So this system will be z dot will be p inverse apz plus p inverse bu. The same system can be represented by this, where P is a constant full rank matrix. How many possibilities is there? Infinite number of possibilities. State variable model is not unique. So we explore these things in your controller design. In the controller design, what we do, sometimes we diagonalize the system and then design the controller. Similarly, if a nonlinear system is not in this form, you transform the nonlinear system into this form. For linear system, you can transform it by suitable choice of P matrix. You can select P matrix, so it becomes controllable canonical form, observable canonical form, diagonal canonical form. All these people who knows control theory, they know it. Similar thing, you can do it for nonlinear system, right? And then start doing it, okay? I will tell you the example how this transformation works. How this transformation works. When my son was studying in school, during that time this, what is that, PS2, PS3, Xbox, this is no longer there nowadays. Is it there? PS2 is there? PS5 works something, because my son is married now, so I'm become old, don't refer that. So he's not playing with that. PS2. So during that time, there's some Xbox was there. He will always say, if I tell him every day I want what I do, I will say no matter what happens, you must study every day at least for 1 hour. And I have got a sheet of mathematics. You have to do mathematics, nothing doing. Nothing doing. And he will always switching, as children, always switching on the television, seeing the cartoon also, always. I went to Professor Virakumar's house. His lovely daughters, younger daughters, always switch on cartoons. It's a universal phenomenon. It's not with. So the father, as a father, you will always get irritated. It's a usual thing, you see. That's a very standard thing in all houses. Xbox, he will never listen to me. He will not do the mathematics. Okay. He'll say, okay, I have done 10, I will not do 20, all these things. So what I do, I keep that particular sheet of mathematics in my car back seat. So he will go to a St. Luke's mall. There's a mall there. Good, big, beautiful mall. In the mall, in the first floor, I park my car. The moment you come, there's a EB Games. The name of the shops, EB Games. Before I enter somewhere, he will straight away enter into EB Games and find out which games are there. Xbox. $135, I remember, during that time, $135, $70, $80, not less than $70. He will say, okay, this game, this is good, this is good, this is good. He said, I will buy it. I'll tell you, wait. I will listen to you. You come to the car, there is a mathematics sheet. You just go and do it. Then we will talk. Now he will go there and he will immediately scribble and do the mathematics, then he will come back. You got a point? Now see here, this child who was not obeying, who was completely in an uncontrollable mode at home, the moment he went to the shopping mall, now it is controllable. Transformation, you see, how easy. You see, I cannot control him at home, but I can control it in the shopping mall. I told that, okay, I will buy you this thing, PS2 games, provided you do these things. You got a point? So similarly, this transformation sometimes works, many times. If it is not controllable here, not controllable in the controllable definition sense, that is not. If it is not possible or it is difficult here, transform. Clear? Do you understand these things? It works in many cases. Many cases, you transform it, okay, and do it in the other domain. Say, for example, this is our home. This is our home, difficult to control. You transform to the mall, shopping mall, see here. And do the job there. Clear? Any time you do the transformation, remember, any time you do the transformation in practice, not in forensic is different, biometrics is different. Any time you transform to other domain, other place, that transformation must have an inverse. You should be able to come back. You should be able to come back this way. If you cannot come back, you are in trouble. This transformation which you are doing, you are applying, it must have an inverse. That means you are going in this direction, you must come back, right? If you cannot come back, it is a problem. Because you are going to shopping mall, you will vanish. Right? I always give this example there also. In India and epics, we have gotten this inverse transformation did not exist in place of Abhimanyu. He entered into the Chakravyuha, we could not return. See, they killed him. It's a serious thing. Inverse transformation does not exist. Clear example there. He entered into the Chakravyuha, do not know how to come. He doesn't know, right? So this is the question of inverse transformation. One-way traffic. One-way traffic. One-way traffic means you are going in one way, you cannot come back. Okay. In linear systems, while transforming, you consider a matrix P which is invertible. That means inverse transformation exists. For nonlinear system, exactly the same thing. The transformation operator, which is invertible, is not told in nonlinear system as a full rank matrix. It has got a name, it is called a diffeomorphism. Geometric diffeomorphism. Diffeomorphism. You use a diffeomorphism T. So Z is equal to Tx. Transform X to Z, where T is a diffeomorphism. What is diffeomorphism? It is inverse exist. Because T may not be a standard matrix which you are talking about. Okay? The same thing, concept is same. So anytime you do the transformation, it must have inverse, right? Not in biometrics. Because there the transformation which you are using should not have an inverse. Should not have an inverse, otherwise people will catch it, people will know it. Nonlinear transformation, that is a different issue. Okay. When a change of variable, Z is equal to Tx is used to transform it because I want to put it in that form. T must be invertible. It must be an inverse map. X is equal to T inverse Z. Since the derivative of Z and X should be continuous, it is necessary that both T and T inverse must be continuously differentiable. And a continuously differentiable map is a diffeomorphism. This is all in the geometric. Feedback linearization is coming under the area of geometric control theory. Okay? See here, I am writing a continuously differentiable map with a continuously differentiable inverse is known as diffeomorphism. So, forget about all these complications. I have got a system that is in this form now. If it is not in this form, I have already made it into this form, then I will design a controller and cancel it. Right? I will cancel. Only small mathematics. Without that, we can talk actually, very small mathematics. Y is equal to hx. Y is equal to hx. So delta h is equal to del h over del x1, del h over del x2 onto del h over del xn. Okay? That is the definition based on standard thing. Standard y is equal to hx. This is a scalar, y is a scalar. So del h is equal to del h over del x1. X dot is equal to fx plus gxu. Now I am defining one thing. Del f, fx means f1, x1 and f2, depending on the number of state variables, right? This is del f1, this is a matrix. Del f1, del x2, del f1, del xn, and simply del fn, right? Now, I need only one mathematics here. I am defining on Lie algebra that is called Lie algebra. This one will take some time to digest, but doesn't matter. LFH, just see this thing. LFH is equal to del H over del X into F. LFH. LFH is del H over X. F is a vector. F is a vector. So del H over X into F. This is called the directional derivative of H. This is called directional derivative of H in the direction of F. Directional derivatives. So LFH is del H over del X into F, right? Similarly, there is a simple thing, LF2H is equal to del LFH by del X into F. Okay, so this way. I am not entering into that thing because unnecessarily you will get bored. So this mathematics I require a little bit. The Lie algebra, simple Lie algebra, directional derivatives. Yeah, no, this mathematics I require, not necessarily you are interested. What you are interested, while deriving that thing, we require this being easier to do this thing, nothing else. Without that also we can do it, but it's always better. Given a scalar function hx, the directional derivative here is defined. Because I need this mathematics. I may not need it, but sometimes it is always better to do this LFH. Lie derivatives, Lie algebra. Lie is the name of the person. Okay, I think they are Norwegian mathematicians or something like that. Which one? No. Lie algebra is not necessarily required for that. Lie algebra is necessary because when you are deriving, it is easier to represent these things. Not necessarily we can represent. Some people, mechanical engineering, have taught it. They say, no, don't teach Lie algebra for feedback linearization. You just teach in normal. That is possible. Okay. But this becomes easier actually. This is only simple mathematics. Not necessarily. See, LF0H is H and this term. Similarly, LGL LFH is equal to LG LFH is equal to, so see from the right hand side, del of LFH by del X in the direction of G. So whatever is there here, G, it will be multiplied here, last. Suppose I will say like this, LG LF2H will be del LF2H over del X into G. Always see the right hand side, entire right hand side you take it and multiply. Suppose I do very Lx1, Lx2, Lx3, Lx4, that is called to derivative of Lx2, Lx3, Lx4 divided by del X into direction of x1. That is the point. Everything from the right hand side you differentiate and put it there, right? This is the only Lie algebra. One thing, relative degree. Then we will discuss a little bit relative degree. Relative degree is, suppose you have got x dot is equal to fx, y is equal to hx, we will define that. Now first let us do a little mathematics. X dot is equal to fx, y is equal to hx. What is y dot? Y dot is equal to h dot into x. I am doing it here, then it will be clear. Y dot is equal to del h over del x into x dot. Because y dot with respect to time, so y is hx. So first I differentiate with the x and x dot. And what is x dot? That is equal to del h over del x into fx. Right? And that is by definition is LFH. Similarly, y double dot, d over dt y dot, so this will be LF2H, right? Differentiation. If x dot is equal to fx, another one mathematics, then I will close it. Other things we will discuss. Now suppose x dot is equal to fx plus gx u and y is equal to x. Again let us do it. What is y dot? I will come back to this point. What is y dot? Now see here y dot. This much only understand. What is y dot? x dot is equal to fx plus gx u. Y is equal to hx. Now y dot is equal to del h over del x into x dot, that is equal to del h over del x. This much of derivation I will do it actually, otherwise you cannot understand, plus gx u, right? That is equal to del h over del x into fx plus del h over del x into gx into u, right? Del h over del x in the direction of f is equal to LFH. Del h over del x in the direction of g is LGH into u, right? That is equal to y dot. Now if LGH is not equal to 0, if LGH is not equal to 0, then you see by selecting the input 1 by LGH minus LFH plus V will give you y dot is equal to V. Clear? Right? If LGS is not equal to 0, then you can select this input and it will give you a linear relationship between output and input, right? And similarly, if it is 0, further differentiate. We'll see to that now. And correspondingly, you will find we'll give an example. I'm not entering mathematics now. How to find out a linear relationship between the output and a pseudo input. That is the objective now. So the idea is, forget about Lie algebra. You have got an output. We'll do it in an example, it will be clear. You differentiate the output until u appears. And then you cancel it. Let us do it, right? And a number of times you differentiate until the u appear is called the relative degree of the system. Let us do an example, then you see. Definition, these things will come later. Now see. Consider the Van der Pol oscillator. X1 dot is equal to x2, x2 dot is this one. Determine the relative degree of the system when y is equal to x1. First let us see. Relative degree is important. I will tell you why it is important. What is relative degree? Differentiate y until u appears. The number of time you differentiate until u appear is the relative order, right? Now y is equal to x1. Let us do it. Differentiate y. So what is y dot? Is equal to x1 dot, right? Y is equal to x1, so y dot I am differentiating once x dot. What is x1 dot? See the equation. That is equal to x2. Is u is appearing? U is not appearing.